All right, so I have a few slides, so I'll move through these kind of quickly, but I really am happy to answer any questions related to this or other topics. But I'm really excited to talk to you guys about science communication. You guys have been doing this, seems like a really great deep dive in this mini series. And I want to share some inspiration from design thinking. And I think this is relevant for science communication as well as many other endeavors in your life, as I will describe a little bit. And we know that science communication is really important, and I really applaud all of you for being so passionate about this, because I think this is, really a key thing in being able to translate. We talk about translating technologies to the outside world, but really science communication is involved in translating knowledge of science to the outside world, which really has a lot of potential for inspiring other people to also follow this path, and has many potential ripple effects. So I think this is a great endeavor. And I wanted to see if any of you guys, to just kind of like set the stage, if any of you recognize either of these products here. We have some Burger King fries here. I don't know, does anybody ring a bell with that? Does that resonate? We got one thumbs up. Well, so I don't know about you, but I never saw watermelon Oreos on the shelf, and I never had Burger King's Satis Fries. Burger King Satis Fries, they thought that this would help if they could come up with a fry that like didn't have as many calories and was like healthier, that people would be able to have more of them without all the calories and like feel better about it. Watermelon Oreos, they thought this would be a great, Nabisco put out this product as a limited edition, and thought this would be a great fun little value add. And few people have heard of these products because they were quickly abandoned. Turns out that Satis Fries, they realized people didn't want to feel guilty about eating their fries or be reminded that they could eat healthier alternatives. You have fries to have your guilty pleasure. And watermelon Oreos, turns out that watermelon does not go so well with the Oreo cookie. So these were insights that they learned by hindsight after having already like fully launched a product. And I think this is really interesting as we, think about marketability, because, even the greatest things can have little impact unless people care. You can have the greatest solution, but in search of a need, it can be a little bit tricky to have things really connect in the best way possible. And this is kind of like what I remind myself about science communication a lot. If your only product is a hammer, every customer looks like a nail. This is one of my favorite slogans. Obviously every customer is different, but if we're so focused on the solution, it's hard to really adapt it and really understand those customers. And so often, some of the approach can be, just to have a louder megaphone, right? We're scientists, we have our insights, we have the things that we discovered in the lab, and we want it to translate, but I think everybody understands that a louder megaphone is not really the solution to that. And so a good way to kind of think about this is a model that's been proposed of, instead of having this kind of, direct translation of knowledge in a very, linear way, that a good approach to this is much more non-linear, right? And it's messier, and it takes time, and it's multifaceted. But this kind of communication will help us be more effective in our science communication over time. And we know that scientists, we work in a world where facts are the driving factor. And I think I'm always reminding myself that I'm communicating in a world where, that's not always the case, right? Facts matter, but it's just part of the equation, right? So the presentation and the style matter a lot. Connection with the society matters a lot, right? It's very multifaceted. Okay, so creativity, I think, is a great approach to be able then to have this multifaceted approach. And defining creativity can be difficult, but this general consensus seems to be that there's two facets to creativity. First is it involves ideas that are original or novel, and second, that these original novel ideas have a place in the world, right? They fit some kind of need to some broad extent. And neuroscience also has a bit of consensus in that definition. And there's really fascinating studies of neurobiology around creativity. And there's even a study, I don't know if you guys have heard about the study that they did on Albert Einstein's brain, but there was a scientist who actually took Albert Einstein's brain without the family's permission, and cut it up into a bunch of different pieces to be able to profile and understand what was it that made Albert Einstein, so creative, so unique, such a powerhouse. And he shared these brain samples with various colleagues, and there were a number of studies conducted, and the results, have met with some criticisms, but they did find that there were increased glial cells in the neural tissue, and different connections were stronger. And there's been a lot of other interesting studies since then as well, looking at different regions. And it turns out that creativity, even in your brain, like the very basis of creativity, lies in making connections, right? It's not in one specific brain region where it's like, okay, let's just stimulate this brain region and then I'll be more creative. Or, let's in the future have Elon Musk's tool in my brain that'll stimulate that area. It's not dependent on just one area. It's in these connections. So there's three networks involved. One is the default network, which is the network that's involved when you're bored or you're not like directly thinking about something. The second network is the executive network, which is network involved in planning and thinking, decision making. And then the third is the salience network, which is what goes in between the two, right? So what is helping you switch between those two networks. Okay, so creativity literally lies in making connections, right? So I think creativity, as well as what we're trying to do in science communication, involves in drawing on a number of different aspects, right? And bringing things together, finding new approaches. And when I think about, what's going to help us to do this better, I think of design thinking, which is, something that I was really enamored with. It was actually one of the main reasons why I went to Stanford for my PhD, is because Stanford was, has great entrepreneurship resources, and then it has the D school, the design school. And at the design school, they teach this process of design thinking that really focuses on the users, really focuses on the people, the customers. And it's three big phases. The first is in understanding your people, and then exploring around potential solutions, and then actually having that materialize into prototypes and things you can test and then implement. Okay, so I thought that I would introduce this to you because I think that, it's helped me a lot, this process. Maybe some of you have already heard about it. And I think it's, really encourage everyone to dive into it. And, perhaps we can use this time here today as a way to think about, how you can apply that to what you're working on currently, or what you want to be working on in the future, because it's a really helpful toolbox. So at the D school, when I was there, I got the great pleasure of spending a year working with David Kelly, who's pictured here. He's the founder of the D school and of the company IDEO, that is very much, the first kind of incarnation of this human-centered design approach. And he really shared some wonderful stories that I think kind of explain design thinking very well. And one that really stuck with me was the bicycle that IDEO came out with. So in their approach to designing a bike, they realized that, at the time, many people were interested in developing a motorized bike, right? Because biking is hard, and, most people are not like pro cyclers where they're really enjoy biking and getting sweaty for extended periods of time. But commuters, want to be able to get to work faster without getting so sweaty. And so there was a lot of interest in the market among other companies to have a motorized bike, but they weren't selling the way that they thought that they would. And so one of these companies came to IDEO with this quandary. And so IDEO conducted a lot of user interviews, right? They talked to people who were commuters. They talked to people who were use bikes for transportation to various activities and events. And the insight that they had was that it's not that people didn't want to bike at all. They wanted to bike. They just wanted, as it were, to feel that the wind was at their back, right? Like they wanted to put in a little bit of effort, but to be successful, right? They wanted that like feeling of accomplishment. And so they designed a bike that is a bit motorized. It provides some mechanical push there, but the biker has to actually pedal, right? So the biker pedals, but with every push that you put in, you get a lot more bang for the buck, right? You go a lot faster with a lot less effort. And so that's actually become one of IDEO's more successful products. And it was all through this really understanding of the customer, right? Through all those user interviews that they did, that finally led to this aha moment, right? This insight of what could really be a cool way to really fill their real need, and not just what they had first on the superficial level kind of assumed as their need. Okay, so breaking it down a little bit, the design thinking process, it is a very cyclical thing. So don't think of this as like, complete stages that you need to complete before you go on to the next thing. But this is the general schematic of this process. And so in the beginning is again, the empathizing, the understanding the needs of the user. This can involve a lot of interviews, shadowing. It should be really not trying to assume any answers or project potential solutions onto those users, but really just trying to understand, right? Trying to understand the whole picture and see things in a new light. From that, then, you can document a lot of interesting stories. You can, try to hit on particular needs, and then define that into, really, really key aspects. And at that point, we write what's called how might we statements, where you're posing the question to yourself of how you're going to solve this problem. So how might we design a bicycle that commuters to work are going to, want to use more? I don't know what, right? But each of those aspects after that, how might we, changes a lot what your solution space can look like, right? So, even if it's, for example, commuters who bike to work, that's very different from bikers in general, or cyclists, or bikers who bike for fun, for leisure, right? So defining this define step here is really important as well. And you want to try to set on pain points, right? So things that really matter to your user. This is like a really good thing to kind of hit on. Okay, so once you define, and again, this is cyclical, so you could redefine, you could have multiple how might we statements that you ideate around. But once you have one, ideation, this is my favorite stage. You get to generate all kinds of potential solutions. And this was, I think, one of the most life-changing aspects of the design thinking process for me, because in design thinking workshops, you're working on these things with a team, and then you go up to a whiteboard and everybody has post-it notes, and they write out potential ideas and they put them up there, and you try to build off of one another. This is what says yes and thinking. is that when somebody puts something, you're not allowed to say the word no, right? And there's no but, there's no no. It's only yes and, right? It's very constructive. You build on things. So people say the most ridiculous things, and then you say yes and put something that you think could be a good or a possible solution as well. And I think this was so helpful for me because I think as someone who's pretty analytical, it's easy to shoot down solutions before they've really had the time to develop. We kind of have like a readout of like if we think it's a good idea or not. And I think I've really saw how powerful it can be just to like let everything come out, right? To like put all the cards on the table before you start shooting things down or before you start, kind of doing the filter part. And so I think this is like really very helpful. And we in these workshops, we'd also have people that would come in randomly, like, they'd come in with like confetti or with like a blowhorn or I don't know what, and you would have to somehow incorporate that into your ideas as well, right? So something totally random, but just having this thing that would get you out of like your ingrained mindset would kind of jog new thinking, which is really interesting. So this ideate, you really generate all kinds of things from that. And then some of those you'll select to move on to prototyping. Prototyping is to really develop something, to hone it, but in a way that's kind of like the minimum needed in order to test it out, right? To get some information. This is something that I found very helpful in some nonprofit work as well as in my lab work. To do short prototypes that will get you information that will inform a bigger thing. You can move a lot more quickly because you're not trying to like design this big grand thing, and which will take a lot longer for you to get any information about then. So prototyping is really key. And then lastly, testing, right? Seeing what works, watching people interact with your solution, with your prototype, and then regrouping from there, right? Again, very cyclical process. Okay, so this is design thinking process. And I want to tell you a little bit about what we're doing at STEM XX Chats, because this totally used design thinking every step of the way and is still using design thinking. STEM XX Chats is communicating the personal side of careers. It's communicating the potential for impact as scientists, and it's communicating how to navigate all of this over time, right? So this is, STEM XX Chats, we're really trying to follow this model, right? That it's going to involve multiple players, that we want to engage everybody over time, long-term view. And I think, everybody knows that navigating career paths can be difficult. There's a lot of silos of specialized information that it can be hard to get when you're, not there. And, often kids, have somebody that they can ask about career stuff, but maybe not somebody who's in the exact thing that they want to do, and often not more than one someone. Often that person doesn't have a lot of time to like write, really explain everything in detail. So there's a lot of barriers here in quality and robustness and getting this advice. And so we want to kind of bring everybody to the same breakfast table, really at the same level, to be able to have a good exchange of information. And we're doing this in various ways, but all are aimed at really having greater understanding, support, opportunity, and inspiration across the board. We're focused on empowering people to build fruitful careers and lives in STEM. Big emphasis on positive impact, through your work and choosing your projects and choosing what you do, as well as in your personal life. And then in breaking down barriers between career stages, locations, and fields. Okay, so in the process of creating STEM XX Chats, we use design thinking a lot from the very beginning. So this all started during COVID. So I was thinking about starting something like somewhat a little bit like this when COVID started. And then everybody went home, and so in order to do this, I called people up, like I was calling people that I thought could be interested, and hearing what they thought would help them, hearing what they're not getting, what they need, right? So a lot of phone calls, a lot of video chats, a lot of surveys, and then we actually launched our pilot program before we had even like really honed in on what we wanted to do, right? Our first application form was basically explaining the goals, and then asking through a series of questions like what you thought would help you to do this, what are things that out of this list, what are you most interested in, like what do you care about the most, what do you most need. And we did this in different iterations, and we're still doing that. We're not even a year old yet. And that kind of iterative process has been really helpful. So we did a 2-month pilot program, June to August, and then really reassessed. And then we started to formalize some of the structure then. And then when we reconvened with some of our small discussion groups in the fall, and so we kind of iterated around the discussion groups as well as the public events that we were having, and really on each level, right? It was a pilot program, it was a reassessment phase, it was a rebuilding phase, and then like a second pilot, basically. So I think this is really an example of how design thinking can help even in the day-to-day and the structural types of innovation, and for something that is really used as a platform for science communication. Okay, well, so in the interest of time, I will just summarize then. That was an example. I think I will leave you with some potential parts of this process that we could think of how it could be, directly applied to science communication. I think being able to really hone in on who exactly is your audience, right? Your audience par excellence, and spending time with them and understanding them, and then defining that audience, right? And defining that, how might we question? And with some friends ideating around potential solutions to that. You do have to filter. I have ideas about that I'm working on an article now about the filter that isn't currently in place in design thinking, but is, out of necessity needs to happen. But from these ideas then to prototype in ways that you can get some information and then that you test. And the best is when you can test with live people, in person, and you can get some information from that. Or, in the meantime, with pandemic things, to do a video chat. But so I'll leave you with this. This is kind of, I hope, some of this is interesting and could be helpful for you moving forward. But yeah, I'd be happy to answer any questions about anything, and wish you guys all the best.
Thank you, Alice. Any questions for Alice? Okay.
I just have a quick comment. I'm a big fan of the design thinking process, probably because I'm also an engineer, and it's sort of embedded into everything I do, even from a personal life to professional life. It's all there. And I think if you are an engineering student just starting out and you haven't been introduced, I encourage you to do more reading on it. The new part here was the yes and part of the design. And I think it's really great advice to sort of have an open mind and hear people out. And I wanted to say that 1 week from today, we're having an improv coach come in, and that's the only other field I think where I've heard that's a really critical part. It's the yes and you can work with someone to achieve a goal if you're both open-minded.
That's great. Yeah, I think there's a lot of improv tools that design thinking has implemented. And I definitely encourage people to like really, read in some of the literature about design thinking, because I think the overview, seems like it makes sense, and many people have seen that, but there's so much like helpful little, details in there. And the same kind of yes and comes into play with the way that user interviews are conducted, and yeah, there's so many really great tricks all throughout. So yeah, but that's great that you're having an improv workshop as well.
Okay, I have a quick question. How does the motorbike try to find out the correct force to help you pedal?
Yeah, that's the magic, right? That's why they're making so much money. Yeah, it's all about the resistance. So they look at how much force is being applied over time, right? So that resistance that the user is facing is compensated in a well-balanced way. Yeah, and it's a feat of engineering that really enabled that sweet spot that ends up seeming so seamless and effective for the biker.
I'd like to try out.
Yeah. Sounds good.
Mm-hmm. Any final questions, comments? Great. Thank you, Alice.
All right. Thank you, guys. Have a good one.
Thank you.
Thank you.
Mm-hmm. Welcome again. Mm-hmm. Our second speaker today is Elisabetta Matsumoto. She's an assistant professor in physics from Georgia Tech. She obtained her PhD from UPenn and was actually a postdoc fellow at Princeton. The research in Matsumoto lab, if you go to their website, is really cool. It's on geometry and topology of soft materials. I think many of us are fascinated by non-Euclidean space, different from ordinary Euclidean space. And her research lab actually reproduce and design all of those funny, great geometries using knitting and weaving on the fabrics, so that mathematics is not that abstract anymore. I get to know her because I started knitting during the pandemic, and I saw a video of her talking about the knot theory knitting. But today she will talk about math, crafts, art, and making. So, welcome, Elisabetta.
Thanks so much. Let me see if I can share screen. Okay, so thanks so much. I guess I wanted to talk a little bit about this sort of theme of putting art into science and then also turning science into art. I'm going to focus on the math side of things because I think it's really beautiful. And so that's what I actually do most of my outreach on, is sort of math accessibility, math, sort of math love. And I think it's sort of sociologically a thing that we're sort of brought up to have a lot of phobias about math, particularly in the US. So for those of you who went through the US public school system, math is something that we are often sort of taught to fear. It's the thing where, there's a right and a wrong, and there's a thing that you have to memorize, and it's not something that's about being creative and questioning and thinking about basically the joys of playing with it. And I think that's something that's actually really different in a lot of other countries. A lot of other countries do a way better job where, like, parents, instead of always reading a storybook to their kids at night, they will also do like a math problem with their kids at night and try to make it fun. And I think one thing that I really find sort of inspiring in the whole math communication idea is that we can try to reignite that sort of childhood curiosity, joy about learning in a lot of people. So I will probably be focusing more on the education side of sort of research and education side of communication, more so than the dealing with policy and talking with industry part of communication, just so you kind of know where I'm coming from. So there are sort of 4 ideas I wanted to touch on. So one is learning math by observing everyday objects, thinking about what makes an illustration good and what the use of medium for your communication is. And talk a bit about visual storytelling. And then I also wanted to talk a bit about using art as an educational tool and sort of trying to foster the idea of creativity in your students and your peers and just random people walking down the street, because I think nothing brings joy to people the way that making something themselves does. I think that's something that I guess I've seen in a lot of my students, and I really believe in the idea of making as a sort of self-affirming process. So I guess I'll start with learning math from every day. So my lab studies knitting. We study knitting because I grew up as a knitter and my mom is a textile artist. And so from when I was a very young child, we would sew dresses together, and, she would get magazines that would, talk about, oh, here's this like technique to make the seam look really good on this jacket, or all sorts of things like that. So I kind of grew up with this folklore intuition of how the clothing type of creative process works. But when you go to translate that into something STEM wise, that's really hard, because there you are trying to quantify creativity. So that is a little bit of what we're trying to do. And I will say that this particular pattern, it's called The Dragon of Happiness by Sharon Winsauer, was something that really kind of inspired me to go down this path. So this is something I made when I was in grad school. And like I had been knitting for ever at this point. I was like, oh, I've seen everything. I make all this complicated stuff. And this particular pattern, she had a stitch that I had never seen. And it wasn't like a variation of a stitch. It was something that was totally new. So I was really curious about that. And so basically what it got me to think about is like, what makes a knit? Like what is something that you can knit? And so basically that kind of set us down this route of trying to turn knitting into math. And so we sort of do that by looking at the process of making. So the process of knitting for me is this. I have 2 needles, 1 in each hand, and I'm basically manipulating these loops through these loops. So like, how do you come up with a concept that makes that mathematical? And I think, as you'll see throughout this, all of my ideas of math are entirely pictures. They're not equations, they're pictures. And so we came up with this kind of idea where the loops on the needles are basically the lower loops together. So this is us, this is our like, illustration from our paper. That's sort of the process of knitting. And for me, I actually thought of this because this is how I fix mistakes in my knits. So I've knit a thing and then I realized somewhere back there, I made a mistake. And so how do I fix this? So there's a couple of things. I can pull out my needles and like rip all of the yarn back down to that mistake. Or I can say, okay, well, the mistake's in this little region. And so what I'm going to do is I'm going to like slowly unpick that region down to the mistake. And then I have to take that mistake and rebuild everything up. So this basically is the mathematical process of how I rebuild my mistakes. And we've sort of formalized it using not theory, but the idea is you want to observe something in the everyday world and think about what the consequences are and what does that mean. And I think this is true of all of us and all of our research. We can sort of think about not just the sort of desktop lab style research, but we can kind of think about, well, if I make an analogy between this and something that I find really fun, like I knit in my free time, or someone maybe does stand-up comedy in their free time, or so, you know, people can kind of incorporate the things, the sort of patterns that they see in things that bring them joy into their research. And that's kind of where I'm interested in thinking about creativity. Okay, so the other thing I want to talk about, I guess part 2 would be what makes a good illustration. So some things are just pretty. Oops, is my video not playing? Well, this was supposed to be a video that plays. But sometimes things are just pretty. So this is, I was supposed to be wearing these, but I forgot to put them on this morning. This is an Alexander horn sphere done as jewelry. This is a way of kind of thinking about a sphere that's sort of infinitely complex, that's a little bit different in 3 dimensions than 2 dimensions. And sometimes things, oh, it is playing now. So this is what it looks like with sort of in 3D. Some illustrations just make us happy. So this is a tattoo that's on my shoulder. So I designed this, my drawing of it, and Royce Nelson independently had made this sculpture. And it's funny because we basically both picked the same parameters for it. Like there's a whole bunch of parameters you can pick, and we both happened to think that the same thing looked the most elegant. So I thought that was kind of fun. So this is just an illustration that exists because it makes me happy. So this is basically a helicoid, or sort of like a spiral staircase that's in hyperbolic space. So a lot of different mechanism, or a lot of different art is really based on medium. So this is kinetic art. And so this obviously is great for 3D printing. So these are things that you want to pick up and play with and understand because you can touch them. And so that's something where 3D printing is great, because it really has this sort of smooth motion to it. Another thing I really love for science communication is the use of fabric. So this, if you look at each of these sort of colored pieces, this set of 6 green heptagons, or the orange ones, or the pink ones, or the blue ones, each set of 6 of those is something that mathematicians call a pair of pants. And mathematicians love using creative, like kind of silly names for things. So this is a pair of pants. And that's in the hyperbolic plane, that's sort of in the Escher style model. But I don't, you know, it's cool, but it's, you know, it's really abstract there. So how do you make this something that people can understand? You don't need to explain to them how to see something if you can make a something. So here's my sewed pair of pants. I guess maybe it looks a little bit more like a diaper this way than an actual pair of pants. But basically what this tells me is I get 4 pairs of pants, an orange one, a green one, a pink one, and a blue one, and I stick them together like this, and then I sort of connect up the edges, and I end up with this object here. This is called the Klein-Quartic curve. And so this is something that you don't need to understand equations. You can just touch it and play with it. And the things that people react to are very sort of primal. Like people love the idea of touching things. Fabrics are something that we cover our bodies in head to toe since the day we're born. And so there's something that are soft and inviting. And that's what I really like about using them for math, is because it's something that people intrinsically feel comfortable with. And then you can maybe push their comfort zone by being like, oh, well, actually this is math. But they don't feel intimidated. They feel like it's a toy, it's something they can play with. Something about, this is another knitting project. This was actually inspired by something someone said on Twitter. So Fabienne Serrier, who's one of the collaborators on this piece, was making these generative scarves. And on Twitter, someone said, oh, I wonder what happens if you make a Mobius strip. So basically this project was us being like, oh, well, that's a cool idea in a tweet. So basically, this is maybe not about communication. So this is maybe not about medium so much as it is about two-way communication. So it is your audience asks you a question, and how can you respond to that in a way that is sort of appealing. So it's listening to what your audience says. So I think this is something that Alice was talking about, is like this sort of empathizing with your audience. How do you come up with something in a way that they want to hear it or want to see it or want to interact with it? So another thing, this is basically a project that was sort of a computer science project. So people in computer science like to kind of come up with these textile constructions. And this is some example of kind of like a bumpy surface. And in computer science and computer graphics, there are these sort of canonical models, like there's the Stanford bunny and things like that. But it seems more appealing if you made this something you can wear. So we turn this idea into, this is a digital model of my body, and then we turn that into a jacket. So instead of this being a computer science project, this is a thing that you can wear and touch and play with. And so I really like the idea of making as a way of letting people sort of understand ideas that would be intimidating otherwise. This is an example of something slightly different. So this is from an exhibition called Brilliant Geometry that was in Edinburgh, I think in 2018 or 2017, sometime well pre-pandemic. So this is about light and shadows and how do you see things you can't necessarily see, like the fourth dimension. So this is walking the audience through, okay, here's how shadows work in 3D as we all kind of understand them, and then kind of introducing them to the idea that these can work in 4D. So this is what's called a zoetrope. So basically there's a strobe light that goes off when each of these, there's, I think, 32 3D prints. One is each frame of this animation. And so the strobe light goes off when they pass a certain position, and it looks like these solid objects are moving in the air. So this is ways of seeing things you can't see. What about seeing things that you sort of can see, but you can't exactly see? So this is, let's see, I'm gonna have to see if I mute this, maybe it won't play. Oh, this is going to play the volume. So this is the VR version of our non-Euclidean spaces. So how do you see something you can't see is, well, you make it so you can see it. So this is something that you can't see in 3D, but here's a computer projecting different pictures into each eye. So this is a space where instead of having 4 squares around, like 4 cubes around one edge, this one has 6 cubes. So the illustration was him walking around 6 cubes or 6 squares on the floor, matching up with 6 different colored cubes in the space. And so here's another illustration from a more recent project. This is a space called nil, which is really confusing and we want to understand more. So we sort of want to understand that by visualizing it. So this is something that mathematicians don't super understand, but by creating these visualizations, you can start posing questions about it. Like, why is it that we see 4 different yellow streaks when there's really only one yellow sphere that I plopped in the simulation? You know, where are these rings of light coming from? You know, why isn't it just like a smooth pattern? Why are there like discrete rings? Things like that are questions we can start asking, but we only know of them because this is a visualization of it. So I also wanted to talk a bit about visual storytelling. So this is an example of visual storytelling. So this is something I put in a lot of public lectures, is basically talking about the soft materials behind why this fancy wedding dress and human intestines are sort of geometrically and elastically quite similar. And it's based on, sorry, come on computer, you can do it. Okay, so it's sort of based on the idea of having something that's stiff and something that's soft, and they're mixing together and they produce this regular geometric pattern. So I think not being afraid of being silly is something that's fun. And I'm super excited that you're having an improv speaker come. That is, I want every grad student in STEM to have the experience with someone who does improv, because it gets you out of your own head and it gets you to be in the moment. And I guess along those lines, this is another visual storytelling thing we do. This is, again, in that three-dimensional space, is you can use your body to explore mathematical ideas. So this is something that if you took like a grad class in differential geometry, at some point you would like derive this thing called holonomy. It's, you know, a ton of calculus, but you don't need the calculus to understand it. What you need to do is to move your body in these simulations. So we turn this into like this silly set of dance moves. So when you're in the headset, you can do this dance and you can actually see the results of this like really hard to understand mathematical idea. So I think part of what I really love about science communication is you can always challenge people about what they expect of STEM. You can make it fun and silly, and that's where the creativity and art kind of come in, because it's a little unnerving to be like, oh, well, this is a really complicated math idea, but I'm really attracted to how beautiful this illustration is. Or, you know, I just did a silly dance move in front of 300 people on stage, and that's, you know, that's dance. That's math. And I think that's something that breaks down some barriers that the public has with STEM, is that it's this serious, there's a lot of math, there's things that they were taught to hate as children. And the idea of making these sort of fun, I think, I mean, you see, I guess the backgrounds of our hosts are perfect for this. I mean, I think I recognize Randy, the pie character from 3 Blue, 1 Brown, and the Minute Earth, like, so these are people who do YouTube videos, and they're just like designed to kind of make STEM accessible to everyone. And these like little bite-sized nuggets that are kind of fun and quirky and make you ask questions. And I think that's something that's the most important thing, is to bring out the idea of asking questions to the public. Like, they should always be curious and try to probe different ideas and things like that. And so this is something I like to do with my students. So I teach, I teach a undergrad mechanics class, and this is a grad level sort of 3D printing and 3D design class. And so the idea of this class is all of the homework and all of the deliverables are things that they have to make. And that's something that is totally different in the science side. I think engineers just definitely have this up on all of us science people, is that, so I'm at an engineering university, I'm at Georgia Tech, and all of our seniors who are in engineering and architecture and everything else have these senior design classes where they interact with clients and they have to make a product. And I think that is the most amazingly beneficial part of their education process, is they're interacting with real clients, they're creating a product that solves a real problem. And it really challenges them in the best possible ways. And we really lack that in physics and in math and in a lot of the science side of things. So this is my like little attempt of putting this back in the curriculum. So our class had 3 projects. The first one was make a box that opens in an interesting way. So the picture on the upper left, I don't really know the difference between left and right, so you'll have to bear with me. Is basically a maze that's inside this little tube. So there's a cover that goes on top and you can't see any of the maze, but you have to solve it to be able to open the box. And then the other one was something, there's the student who made this was from near Chicago, and that was really important to her. So she made a box that was Illinois, where there was a little lock that was the city of Chicago. The second project was make a mechanism. So anything that sort of moves in this predictable mathematical way. So the top one is an iris mechanism. So this is, I don't think this is actually the way most cameras work because they rely on soft materials, but there are types of lenses that work this way. And then there is a student who, the ones that say C and D, built a robot. And this was really fun because he's in a robotics lab, but was only a programmer, never touched building robots. And so it took him into this class before he ever built his first robot. So I think that was kind of fun. And then the last project is completely open. So this is basically letting people play. And these are 4 examples of different ways that people kind of embodied play. So the first one, this was designed for this student's, I think, 3-year-old nephew. Oops, I don't know why my movies aren't playing. Oh, there we go. Well, this is supposed to open in and out. So it's like this little snake that pops in and out as you open and close the box. So this was a toy, and it was sort of designed to be broken because it's a very destructive toddler. But it's still about play. The one on the bottom left was supposed to be a zoetrope cake, but the zoetrope part didn't super work out, but the cake part totally worked out. So she made these cookie stamps that were based on rotating gears. And that was her final project. And the cake was absolutely delicious. I guess on the lower right, the student made a clarinet with 3D printed reeds. And you could play it, and it sounded awful, like a duck cracking. But we did have people who actually could play clarinet in the class. Actually, not the student, but some other people did, and they were able to like play notes on it. And it sounded awful, but it did play the notes that he programmed it to, which was really fun. And in the upper right, this student absolutely loved this video game, StarCraft 2. And this was one of his favorite characters from it. So he literally hacked his own copy of the game, found the model that they used in the game to animate this character, and turned it into a 3D print. So this is all sort of people expressing things that they love, using making as a creative step. And it's not something that just has to happen with students. This is a series of things where basically a bunch of professional adult mathematicians got to do the same thing. So this was a program at ICERM, which is at Brown, in fall 2019, basically where we had a giant sort of playroom that had a bunch of 3D printers and laser cutters and things to cut fabric and all sorts of whatever you want creatively. It was basically our makerspace that was just for mathematicians. We had VR set up, we had cameras, all sorts of things. So these are a whole bunch of, this is from the website iam.iserm.brown.edu. So there's all sorts of projects that people had. So this was all about questioning what does making tell you about these ideas? How can you use making to explore these different ideas? And so there's also a workshop, which is this summer, so the 19th to the 23rd of July. I'm not 100% sure if we're still accepting applications or not, but there's a website for that if anyone's interested in signing up. It's all about, there's a bunch of workshops on different types of making, whether it's making interactive videos or learning different like 3D animation techniques, learning how to use like CAD CAM software and hardware, things like that. So I guess I will wrap it up there, but thank you so much. I hope you find fun ways of using making creativity, just bring things that you love outside of academia into your communication skills. I think that's a way that everyone just appeals so much. When you're excited about something, that makes everything you say just that much better to people. So if you really love something, I think that shows. So good luck with your communications.
Oh, thank you, Sabetta. I'm so amazed.
Amazing. Amazing.
Yeah.
I'd be happy to take any questions. Oh, I need to turn up my volume again. Sorry.
Hi,
Sorry,
I actually went to Brown University for undergrad, and I was there in person to see the ISERM exhibit, and I think it was really great that you showed some of it here. Like also at Brown, I was taking like calculus my first year, and the professor brought in these like 3D printed models to help us understand like 3D calculus dimensions, right? I was wondering like what place you think like these things have in like teaching math in like a classroom, and not just trying to like get the general public to understand or appreciate some of the beauty of it.
Oh, I think they're incredibly important in the classroom. I think precisely for the same reason that they're useful for the public, is because it gets you to think about things in a different way. It's not thinking about equations as these sort of dry manipulated things. It's getting you to think about the math concepts in a kind of holistic way. So the 3D prints to look at like, this is what a cubic surface looks like, or those are so useful because they show you things that just drawing them on a computer or using GeoGebra aren't going to do. So having, you can be like, oh, well, clearly I just can take like a string and there's a straight line when I do this on my surface, and you can play with things. It doesn't have to be just something that you see from equations. It's something you can touch. And I think the more senses you can bring into education, the better, because like, I mean, memory is a whole brain process. So the more you can engage all sorts of different parts of your brain in the learning process, the more it's going to kind of click for people, and it's going to click in different ways for different people. So I think 3D prints, animations, cartoons, anything that breaks out of the little like I'm writing equations on the chalkboard box is great for math education. I think those 3D prints are excellent. I think there's some that are even painted with like chalkboard paints. You can like draw pictures on them and stuff. Those are great because it gets you to not think, you're not thinking inside the equation anymore. You're thinking, like, mathematics loves thinking about concepts. They don't like thinking about specifics. So thinking about concepts is what you're learning to do. It's bringing you into a mathematical way of thinking kind of without knowing you are.
Right. And like, I guess, what about like, I think physics and math sometimes involve like problems like higher dimensions, which are not like directly related to like 3D space. It's like, how, like, if people find analogs for like those higher dimensional things in 3D space, but they're like things that are lost and trying to simplify it that way.
Yeah, there are definitely things that are lost because you're always going to be projecting out some information. I think there's a really kind of great lecture by Henry Segerman that sort of gets you to think about this. It's like, okay, so we see 3 dimensions. And so imagine now you go down to like 2 dimensions. What information do you lose? How do you represent different things? And then you can kind of take the analogy of what are you losing into higher dimensional spaces. So when I do this, I'm losing this information. When I do this, I'm losing this information. And then I guess the question for students is that information I'm losing important, or is that information I can lose not so important? And I think this is something that's super important in data science, because they will have such huge high dimensional data sets and they want to come up with like a take home message. So learning how to project that down to something we can see without losing information content, I think is a huge research problem for them. So I don't think it's a solved problem at all. I think this is something it's great because it's both something that's useful in class, but it's also something that's a research topic too.
Thank you. I have a quick comment. Well, for me, when I learned Klein bottle, it's always made of glass. It's hard. And it's the first time I see a Klein bottle made by soft fabric. Well, it strikes me that there's a little difference in how you present a mathematical idea. There's a huge difference in psychology. I feel much welcomed and warm. Yeah, it's a fabric.
Mm-hmm.
Mm-hmm.
Absolutely. I think that's such a spot on observation. Mm-hmm. Yeah, how you approach things definitely, or how you present things gives you a different emotional response to how you're going to process that information. So, I personally love the soft cuddly things approach, because that sort of, everyone kind of remembers being a child and having their favorite teddy bear, and that sort of thing. You're more open to ideas, I think, when you have that approach. You're more open to new things, because like when you're a kid, you wonder about everything. Nothing is sort of off limits, and that's something that I think gets sort of almost bred out of us, is thinking, along the, oh, you shouldn't ask questions about that, just take it as fact, or you can't say you don't know. And that's something I think that's awful in our education system. We should always encourage people to say, I don't know, and why. Those are things that everyone should always be asking.
Great.
This was so fascinating. I have a million questions for you, but in the interest of time, I'll let you go. I think I just have one question that I want to get out of my head. When you were showing the pair of pants, and then your sewn version of it in a wrapped around ball, I was thinking, as a materials person, that's like a great drug delivery coating. If you could take a sheet of nanomaterial and then just wrap it in that certain way, you could probably get a slow release of like insulin deliveries. And I guess my question is, how easy is it to have people that are in the research field have an open mind to this sort of soft and fuzzy approach that you're citing? Is it easier? Is it getting easier? Or is this something that you think is a mission that you have?
Oh, that's a great question. That is an absolutely fantastic question. And I think my answer is, I don't really know. I think because I am kind of I'm on the soft materials side, sociologically, like the history is we never quite fit into physics, and we never quite fit into chemistry, and we're not really trained as engineers. So there is a little bit of not fitting in. So it's okay to be different. So I think that's something that kind of goes along with this culture of soft materials. So I don't think for them it's that hard to have something that is warm and fuzzy. Everything is just an approach that is different. And I think they've been put into a position where being different is okay. So that's not a thing that gets questioned. Other types of physics are super rigid and have you're not allowed to ask questions, and everyone uses those like cryptic like vocabulary, and it's like the secret handshake kind of club. And I think then those people would not be so open to it. But if they want to not turn into sort of the dinosaurs of the field, if they want to bring in new creative blood, then I think maybe adopting different communication approaches would be useful for them. Like if they want new students to come in and have new ideas and not just have ideas that are sort of brought down the generations, then I think any type of creative approach serves them really well.
Yeah, it's time. All right, thank you so much, Sabetta. Thank you everyone who hung out a little bit longer. And again, we'll see you next week for improv. Sabetta, you're welcome to come back.
Oh my gosh, the improv thing sounds so much fun. I normally have a meeting with a student right now though, but
thank you.
Anyway, thank you so much for inviting me. This was really cool. I really liked Alice's talk too. It was just fun how different the approaches are.
Yeah. All right, thanks so much. Hope to see
Thank you
you
so much.
Bye.
Thank you for inviting me. Take care.